Welcome to Math 2318, Section 4.5. In question 1, we'd like to form a subspace here, and we'd like to figure out, well, what's a basis for it and what is its dimension. So it's of this particular form. We have s minus 5t, s plus t, and 7t, and this is for s and t in R. So I took that down here, scroll down a little bit. So I took that form and I split it with all the stuff that had S in it, all the stuff that has T in it. And so you can see that everything in the subspace is a linear combination of these two vectors. These two vectors are linearly independent and they are our two basis vectors. Since there are two basis vectors, the dimension is 2. In question 2, we have much of the same. We have things of this particular form of A and B. So again, same basic strategy. There are only two letters, A and B, so I'm going to split this into all the things that have A in it, all the things that have B in it. And so what I see again is I have a linear combination of these two vectors. They are the basis for the subspace, making the dimension 2. In question 3, we'd like to find the dimension of the subspace of all vectors in R7. So here's a vector in R7 with 7 components, but there's a restriction, and that is the 4th and 5th entries are equal. So you see here down in the 4th and 5th entries, they are exactly the same. So we have the subspace H consisting of everything of this particular form. So what that means is I'm going to split it with everything that has A in it, B, C, D, E, and F. A, B, C, E, and F are essentially our normal basis vectors for Rn. It's only D here where it is repeated in the 4th and 5th place that you have 2 1s. So how many of these vectors are there? There are 6 basis vectors, and so the dimension is 6. Alright, what about in question 4 here? The dimension of the subspace spanned by these 3 vectors. Well, if you look at it for a moment, you'll realize that 2, 8 is just a scalar multiple of the first one, 1, 4. Namely, 2 times it is 2, 8. And minus 4, 16 is really minus 4 times the first one. So only one of them is unique. The other two is a scalar multiple of the first one. So H is really spanned by all multiples of the vector 1, 4. There's only one of them, so the dimension is 1. All right. In question 5, we want to find the dimensions of the null space and the column space. Well, let's see. What size is this matrix? It has 4 rows. It has 5 columns. Therefore, it's going from R5 to R4. So the reason I do that is I know that the dimension of the column space cannot be any more than 4. It could be less, but it can't be any more than 4. So let's see, what if we take the matrix A that we're given? I'm going to clean it up just a little bit because I'm interested in what does the null space look like. And so I keep on simplifying that, using row operations to get 1s and 0s. And so what I see is x5 is 0, x4 is 0, x3 is 0, x2 is free, and x1 is 2 times x2. So the null space consists of all vectors of the form of a scalar times 2, 1, 0, 0, 0. And so what I see, since there's only one of these, the dimension of the null space is 1. How many pivot elements did we have? Well, we had 1, 2, 3, 4 pivot elements. So the dimension of the column space of A is 4, which is the dimension of the space it's going into. All right, in question 6 and 7, I wanted you to look at something that's important in mathematical physics. And that is the first 4 what are called Hermite polynomials. 1, 2t, minus 2 plus 4t squared, and minus 12t plus 8t cubed. So it comes about in certain differential equations in mathematical physics. We want to show that it forms a basis for P3. Now, P3 was all the polynomials of degree 3. The normal basis we are familiar with, we've seen it before, consists of 1t, t squared, and t cubed. All right. So what they're saying is, how are we going to go about doing that, and what theorem do we use? So any p-dimensional vector space, any linearly independent set is automatically a basis. So they actually step us through the process. So here's our standard basis for P3. All right. And so what they say is, let's take each of the Hermite polynomials and write them in terms of the normal basis. So 1, well, that was my 1. 2t is really a 2 in the t position. The minus 2 plus 4t squared, so I've got a minus 2 in the constant one and a 4 in the t squared, and so on for the last one. So how do we show they are linearly independent? We form a matrix and show that the number of pivots matches up. So what you look at when you look at the number of pivots, when you put these in, these were the Hermite polynomials, in terms of the standard basis, we have 4 pivots, and so they are linearly independent, and the dimension is 4. In the last question, we have another set of polynomials called Legendre polynomials, again from mathematical physics and certain differential equations. And again, they're a set of polynomials of degree 3. We want to show again that they are another basis for P3. So we basically do exactly the same things. We take these polynomials, write them in terms of the standard basis. So you see how they would look in the standard basis. The last one here, you see 6 is the constant, minus 18 is for the t, 9 for the t squared, and minus 1 for the t cubed. We take them, put them into a matrix, and look to see how many pivot positions that we have. And so you see, here's the what they would look like in terms of the standard basis. We again have 4 pivot positions. So the columns are linearly independent. There are 4 of them, so the dimension of the space is 4. So just wanted you to be able to see some important polynomials from mathematical physics and how they do come up even in linear algebra.